Hello, so in this video, in the start of this chapter, we're going to look at exponentials. So these are expressions of the form y is equal to a to the power of x. So here we're going to look where x is a power, not a base, like x squared or x cubed or whatever else. So now x is in the power role, not in the base role, okay? And we got a constant base a. So you would have seen at GCSE perhaps what the graph a to x looks like, but let's go over it in more detail. So firstly, we're going to consider when the base a, so again, the base is the number right at the bottom, and then the power or the index on top, okay? So that's the terminology. The base a, when it's greater than 1, okay? So for example, let's take 1.01 to the power of x, okay? A very, very small number greater than 1, okay? 1.01. So what I'm going to consider when we're working out the graph is the type of values it takes. So, firstly, what happens when x gets bigger? Okay, let's investigate that. What if we have 1.01 when to the power of 10? Okay, if we did that to the power of 10, we get 1.104, blah blah blah. Nothing exciting, right? It's 1.1. It's got bigger though. It's got bigger. It was 1.01, but when I times it by itself 10 times, it's 1.1 now. Okay, not 1.01. Interesting. What about if we raised it to the power of, let's say, 100, right? Now we get 2.704. Okay, so it's got a noticeably bigger, but still not much. Gone from 1 to 2 when we times by 100 times. Right, it's a slow growth, right? It's slowly going up. What if we then did it to 1,000? Do it to 1,000 now. We get 20,959.15 blah blah blah. So it's got a lot bigger now, right? All of a sudden. Let's say we do raise it to a power of 100,000 then, right? Actually, you get math error. And the reason for that is because it's too big. The calculator physically, the number's too big now. So we get math error there. Okay, but actually, let me do one less. So that was 100,000. I'm going to say too big. Okay, too big for the calculator. If I did to the 10,000 instead, not 100,000 but 10,000, we get 1.63 to the times 10 to the 43. So there's basically 43 zeros here. So this is almost like 163,000 blah blah blah, and then there's 43 zeros, right? It's in standard form. So it's a huge number, right? Absolutely extraordinarily big number, and then we just basically, it's too big if we keep raising the power. So what do we notice is originally there's a slow growth, right? There's a slow growth, but eventually it's what we call an exponential growth. It rises it goes up very sharply, very quickly. Okay, hence the name exponential, right? Exponential. So what's happening is eventually it's tending to infinity. Okay, so when I say too big, it basically means it's tending to infinity. Okay, so what that means is in the long term, if I draw a little rough sketch, it needs to shoot up like this, right? So you can see at the start there's a slow growth. Right, it's very slowly going up, and then it shoots up. It shoots up, right? That's an exponential growth, okay? So that's what's happening when x gets bigger to infinity. But what about then? What about when x goes to negative infinity, okay? Well, actually, if we then said, if we went the other way and instead considered negative powers of 1.01, so 1.01 to the negative 10, Well, if we use our index laws, we could say that's 1 over 1.1 to the power of 10. So that means basically, in this case, it'd be 1 divided by 1.104, because that's 101 to the power of 10. And so if we work that out, I get 0.905. So actually, it's this 0.9 is less than 1.01. So what you will find out is, as we have more negative values of x, conversely, rather than increasing, we decrease it. The value we get is smaller, okay, than 1.01. What about if eventually we did 1.01 to the power of negative 10,000, right? What if we did that? Would that be, again, reciprocal of 1 over 1.01 to the positive 10,000, right? Remember your power laws? If we did that, we get the other way. So we get 6.113 times 10 to the power of negative 44. So because it's a negative power, remember your standard form, that's basically like 0.0000, like 44 zeros, then the 6113. So it's incredibly, basically 0. Okay. And then if I... and yes, so that's basically what happens. Hopefully you notice when it's negative infinity, as we get more negative, the values of x goes down. As you can see here, it actually goes to 0. It doesn't go to negative infinity. It's not a negative value. It's positive, but it goes to 0. So actually what happens is, if I look at my curve up here, as x goes to negative infinity, to the left, that way, it would actually just slowly, it would just go towards 0, right? It gets closer and closer to 0. That is an asymptote then, okay? Because remember when we looked at reciprocal graphs, for example, asymptote is a line where it tends towards it but never touches it or reaches it. So the asymptote is when y is equal to 0, which is the x-axis, okay? So that's the graph, right? That is the graph. Right, that is the graph of for example 1.01 to the power of x, right? That's the behavior, okay? Hopefully that made sense when as we experimented with the numbers. That's the type of exponential graph, okay? So the last thing actually to note is what's that intersection point with the y-axis there, okay? What's the crossing with the axis? Well, because it intersects the y-axis, that's the y-intercept. Remember, that's when x equals 0. So if I plug x is 0 into 1.01 to the power of x, that'd be 1.01 to the power of 0. Anything to the power of 0 is 1. Okay? And so that would be 1 there. Okay? Cool. Okay, and actually then, that generalises, the same concept applies for any base A. As long as A is greater than 1, it has this shape here. So in summary, what happened, this is the sort of shape we get. A y equals a to the x, where A is above 1. Okay, A is bigger than 1. And it crosses the y-axis at 1 as well. Okay, so why am I making a bit of a point about A greater than 1? What about when A then is less than 1? Well, actually, it's the opposite way around. It kind so how we discussed here. Well, actually, no. Let me do an example. If A was less than 1, let's take, for example, 0.99, right? To the power of x, right? Y is equal to a to the x. Let's take a to be 0.99. Again, if we do our sort of investigation, let's take 0.99 to the power of 10. That would be 0.904. So it's getting smaller. Hopefully you notice it's smaller. 0.90 compared to 0.99. Then if we did 0.99 to the power of 10,000, let's say, again we have this 0.000 blah 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 248, and there will be about 44 zeros there. Okay, so it's extremely small. Okay, so actually it's going down, but it's a similar effect, right? It's tending to zero. Okay, hopefully you can notice as we increase powers of x, you can test it yourself, eventually it's just going to go to zero. That's what the value is tending towards. Okay, and then what about if we did the other way around? What if we did negative, say 0.99 to the negative 10? Well, we could do the reciprocal then. So it's 1 over 0.99 to the power of positive 10. So again, hopefully you kind of notice if we're dividing by a number less than 1, but so this would be 1 over 0.904. If we did that in a calculator, we get 1.106. So it's actually bigger now. It's gone bigger than 0.99. And then if we did 0.99 to the negative 10,000, let's say, that would be 1 over 0.99 to the positive 10,000. That would be 4446 blah 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 000 with again not 43 zeros. Okay, roughly. So it's extremely big. Okay, it's extremely large number, right? And so then it has the opposite effect. Okay, so with this graph, when a is less than 1, it has the opposite effect. So as you can see here, when x is positive, when x gets bigger, the results it decreases, right? Which means when x goes to infinity now, that way, the graph gets smaller. Okay, so it looks something like this, and it will tend towards 0. So the asymptote will still be at 0. So y is equal to 0. And then when x is negative here, when x gets more negative, we can see the result is it just blows up to infinity. Okay, so it tends to infinity. So then as x gets it shoots up like that when x goes to negative infinity to the left. Okay, so that is the graph. So if I draw that graph then and compare it with when a was greater than 1, if I then do a greater than less than 1, the graph is kind of reflected, right? So it looks a bit like this. And there we are. Okay, so you can see that the two graphs are kind of reflected in the y-axis there. Okay, and so these two, you need to be aware of the distinction when the base a is greater than 1 and when it's less than 1. Okay, so yes, you need to remember the graph a to the power x when a is greater than 1 and when a is less than 1. Okay, so I guess one question you might have, what if a equals 1? So what if a equals 1? If we have that, then y would be 1. Then y would be 1 to the power of x. But of course, 1 to the power of anything is equal to just 1. So what you'd effectively have is literally just the line y equals 1. So it's nothing special, really. But anyway, yeah. So those are the two graphs you need to remember, ideally. So yes, okay. Okay, so now we've got some examples. So here we need to sketch on the same axis, on the same graph. The graph y is 3 to the x, y is 2 to the x, and y is 1.5 to the x. Okay. So right. Firstly, let's do 3 to the x and y. Well, 3 to the x, again, a to the x, if a is greater than 1, which they all are, we've got 3, 2 and 1.5 as the base, that's great. It's going to have this sort of shape, right? it's going to go up like that, okay? So that means, well, it's going to take this sort of shape then, right? Up there, okay? And then it'll pass through the y-axis when? So the y-intercept, again, when x is 0, we set x to 0, then y would be 3 to the power of 0, which should just be 1, because anything to the power of 0 is 1, okay? Okay, now we've got to plot 2 to the x, okay? We've got to draw that. Now, 2 to the x compared to 3 to the x, 2 to the x is smaller than 3, which means the graph of 2 to the x will rise and go down and go up more gradually than 3 to the x, okay? For example, 3 cubed is bigger than 2 cubed, right? The same base, the same power of 3, for example, if x was 3, well, you can clearly see the bigger number 3, the bigger base, means it will just rise and be bigger in general, okay? So what that means is it changes more slowly, 2 to the x. So it's going to look something like this. It's going to start off a bit above 3 to the x, but it still hit 1, and then it's something like that, right? It rises and goes down more slowly, okay? But it will still pass through 1. That's the key feature, because if I set x to 0 for the y-intercept, we would have 2 to the 0, which is still 1, okay? And so, yeah, then we have 1.5 to the x. So again, it's the same sort of idea. It will rise and go down more gradually than 2 and 3. So it will look something a bit like this. Change that again. Something like that, right? So you can see it's a lot less steep, essentially. And so that'll be 1.5 to the x. Okay, and again it passes through 1. Okay, that's the key y-intercept there. Cool, so hopefully you get that right. As the base increases, so if we go from 1.5x to 3x, it will become more steeper because it's a bigger number, so it will just go up quicker. Okay, now we have, we need, on a different set of axis, we need to sketch y is a half to the x and 2 to the x. Okay, so y is half to the x and 2 to the x. Well, firstly, we know what 2 to the x looks like, so I'm going to sketch 2 to the x first. We just did that, right? So 2 to the x again will look something like this. There we are. And it will pass through 1. Okay, then what about this half x? Okay, now there are 2 ways. Again, you could just see that a half is effectively, well, it's less than 1, right? So a is less than 1 because it's a half. So it has the opposite effect. So it comes down like this. And it'll still pass through 1, and it will tend to 0 as it goes to positive infinity. Okay? Something like that, right? That'll be y is a half to the x. There, okay? Again, as we go back to our previous example, that'll be what it looks like when a is less than 1. So in this case, we've got a half. Okay? So it's it's a reflection, effectively, in the... It's a reflection in the y-axis, but we can also just do a bit of power law manipulation. If we didn't realise that, that's fine. But what we can do instead is say that y is a half to the x. We can use power laws. So firstly, this is a half. We can write that as 2 to the power of minus 1. Right, it's a reciprocal 2 to the power of x. That's then 2 to the minus x. Well then, if we then compare that to 2 to the x, so if we called f of x equal to 2 to the x, then 2 to the minus x is f of minus x, right? But what do we know if we look at graph transformations? If I get rid of this half to the x, right? If I was to... So what I'm doing is, if this is my f of x, right? This 2 to the x, right? If I'm then plotting f of minus x... So remember, when we looked at graph transformations, f of minus x, because it's inside the function, we're doing the opposite to what we expect. What do we expect is that we're going to multiply the x coordinates on the graph by -1, but instead we divide by -1. Well, actually that's the same thing, really. So basically that means we're going to multiply the x values by -1. Again, remember when we did graph transformations. Alternatively, you could remember that is reflection in the y-axis, but let's go with what with this philosophy here. So if we're multiplying the x values by -1, so for example, this point up here would then map across the y-axis to here, same as that point here. Okay, so those are my new points, and then this point here would, because that's on the negative y-axis, will then be on the positive y-axis there. Okay, so if I do a sketch between these 3 points, let's say, because the whole idea is I want to see where the points map to under this transformation. If I do that, then there we are. Well, obviously it'd be somewhere there, right? But there we are. That would be my graph y is a half to the x, which was the same graph, right? And you can see also that's a reflection in the y-axis. Okay. So yeah, you can do it 2 ways. You could either just memorize that at half to the x, because it's a half, it's less than 1. It would be the opposite graph. It'd be reflection instead. It would go down instead of going up. Or you could convert it to powers and then say it's f of -x. Okay, then reflect it in the y-axis in this way. Okay, so yes, you do again need to be confident in your graph sketching and even your transformation skills. So again, this is good practice, but yeah, hopefully that sort of makes sense. Okay, so now we've got this question, very sort of similar question. We need to sketch the graph of y is a half to the power of x -3. Okay, right. So okay, so okay, so it's not half to the x. We've got half to the x -3. So this is going to probably involve graph transformation. So I'm going to need to probably split this, sort of simplify this in a way. So if I do half to the x -3, I can do the same sort of thing I did before. Well, firstly, half is 2 to the power of -1. Then x -3. Then I can times, again, because now I've got these brackets with powers outside, I can multiply the powers together, because that's an index law. So then that's 2 to the -x, and then -1 times the -3 is add 3. And so actually what we can do at this point is actually then split this up as 2 to the -x times 2 to the 3. Okay, again, I could split up the powers in this way. Again, remember your index laws. Because then if I was to times these two numbers, I add the powers to then get back -x add 3. Okay, but then actually 2 to the 3, that's 2 times 2 times 2, that's 8. So I get 8 lots of 2 to the -x then. So then actually I know what 2 to the -x looks like, because I know firstly what y's 2 to the x is. Okay, but again, that's just my sort of graph here. Y2 to the x is 2 is bigger than 1, so it's going to go up, as we discussed. It's going to go up, so it has this sort of shape. But then if we then 2 to the -x, as we discussed, is going to be reflection in the y-axis. Okay, so it's going to instead come down like this. Oh, there we are, something like that, right? And that'd be y's 2 to the -x. Okay, and then I need to sketch 8 lots of 2 to the -x. Okay, so then hopefully you recognise that really our graph 2 to the -x is going to be effectively times by 8, and the 8 is outside the function, if you will. It's outside the 2 to the -x. So it does what we expect. It affects the y values. So the y values are basically going to times by 8. So for example, this where it crosses 1 here would then cross to 8, effectively like that then. And then effectively the graph is going to be a lot more steeper because the values are bigger. So it's going to look something like this. And that would be y is 8 lots of 2 to the minus x. Okay. And that's it. Okay, that's what the graph will look like. Something like that. Then it says give the coordinates where it crosses the y-axis. Well, we already did that, right? We said that effectively, because 2 to the minus x crosses at 1, then 8 lots of 2 to the minus x will cross at 8, because the y coordinates are times by 8. Alternatively, to find that, if the y-intercept then, again, that's when x is 0. So if we have y is 8 lots of 2 to the minus x, no, actually, if we took the original graph of a half lots of x minus 3, it's the same thing. It's the same thing, right? But if I'm going back to basics, so if I have this default equation I was given, if I set that to 0, x to 0, that'd be a half of 0 minus 3. That's about half to the minus 3. And then you could perhaps put that in the calculator or simplify it yourself if you want to, using power laws. But we get 8. Okay, we get 8. So that indeed I must be correct then, right? In that regard. So yes, so that's a graph. So again, you need to be comfortable with the idea of spotting and you applying graph transformations. Okay. Again, we looked at that in chapter 4. But yeah, we can now sketch exponential graphs in this way. Okay. Right, so we've got some exercise questions then. So we're given the graph of y is ka to the x, and it passes through the points 1, 6 and 4, 48. Find the values of the constants k and a. So actually, we have the graph y is ka to the x. I'm told it has these 2 points in. So firstly, I'm going to sub the point 1, 6 in, right? Because that's the point is on this curve. So that means when x is 1, y is 6. So y is 6, that equals ka to the 1. Okay, because x is 1. But that's just ka then, right? I also then going to sub in the point 4, 48. So if I do that, that means when y is 48, I'm going to get x is 4, so ka to the 4. Okay, so from this, I need to find k and a. Well, actually, these are simultaneous equations, right? 2 equations and 2 unknowns. How can I solve this then? Okay, well, it's a bit of an unconventional simultaneous equation. I don't think we've seen much like it so far. But what you can do, I mean, you could substitute if you wanted to. It'd be a bit cumbersome. I guess, for example, you'd have to, let's say if your 6 is ka, you then divide by, let's say, a to get 6 is 6 over a is equal to k. Then you would sub k into the other equation, and so then you'd get 48 is going to be ka. What we know, k is 6 over a, lots of a to the 4. That's 6a cubed, okay? Because then the a here will cancel with an a of a to the 4. And then I'll get a cubed is 48 over 6, which is 8. And so if a cubed is 8, that means if we cube root 8, that would be 2. Okay, so a is 2. So now that we know that a is 2, therefore k is going to be 6 over 2, which is 3. And those are my values of a and k. Right? A is 2, k is 3. Alternatively, that is, I guess, a sort of safer option. It actually doesn't work all the time, depending on the equation, but you can try and substitute if you're a bit uncomfortable. Just it's kind of, I guess, a systematic, safe way of solving it. Alternatively, we could just actually divide the 2 equations. So if I divided the second one by the first one, let's say, I'd have ka to the 4 divided by ka, because that's the second one divided by the first one, right? And again, then that'd be 48 divided by 6. And so actually the k's cancel here, and a to the 4 a to the 4 divides by a to get a cubed. And then 48 over 6 is 8. And then we get to the same sort of process as we've seen here. So again, a sort of a weird equation, a weird simultaneous equations, but there actually are multiple ways of approaching it, okay? Whatever you find best, but there we are. Okay, we've got this question here. So we're given the graph of y is pq to the x, okay? We're told it passes through these 2 points. And it says, by drawing a sketch, explain why it's between, q is between 0 and 1. Right, okay, so it says drawing a sketch. So actually, the only thing we have to work with, well, we obviously got the equation, but we don't know what p and q are. But we're given the 2 points. Let's plot these 2 points. So -3 for x. We get 150 for y. That's going to be absolutely massive. That's going to be up there somewhere. Let's just say, right? So that'd be 150 for y. So if I plot that point, then if I plot 2, and then that's 0.048, that's basically on the x-axis essentially, right? That's going to be 2, 0.048. Well, actually, then you can spot then it's going to come, it's also going to be, it's still going to be an exponential graph, right? It's still going to be an exponential graph. So either it's going to look like that, or it's going to look like that, as we discussed. And this graph is positive, it's going up. That's when a is greater than 1. And then this will be when a is less than 1. Again, this is the graph y is a to the x, okay? Again, you need to remember these 2 cases, as we discussed at the start. Well, actually, if you look at these 2 points, if we were to draw a curve, it would actually resemble the latter, right? Something like that. Not the best graph, but you get where I'm coming from. Actually, let me draw that a bit again. There we are. Much nicer. So it actually resembles this graph here. It comes down. But then that graph occurs when a is less than 1. So in this case, q, our base of x, our base is less than 1. So because the graph is decreasing, the exponential graph y is pq to the x means that it has to be q is less than 1, but actually it also means it has to be above 0, for the simple fact we don't really need to consider when q is when a in general, when a is actually 0, because obviously if y is equal to 0, then obviously it's just y0, it's nothing, right? If we add 0 to the x, that's still 0. So you know what I mean? So 0 doesn't really matter, and if it's negative, we just whack a negative on. So if we add a to the x, if a was negative, we could just say minus a to the x, and then do it that way. So it doesn't actually matter. So actually, technically, a is less than 1 in this graph is actually when a is between 0 and 1, but it doesn't really matter. But that explains that condition. Okay, quite a tricky one that was. So that's the reasoning. Okay, part B. Again, now we need to find the values of p and q. So again, it's the same sort of idea that we got these 2 points, right? We got these 2 points, so we're going to substitute them in. So y is pq to the x. So I'm going to first sub in the point minus 350. 150, sorry. So then that means that y is 150, pq to the x, which is minus 3. Then I'm going to sub in the other point, which is 0.048. So if I do that, that means when y is 0.048, that'd be pq to the 2. So then I need to solve these. So if I call them 1 and 2, again, what can I do? I could either use substitution. I could rearrange to substitute one into the other. But actually, if I then divide the second equation by the first one, I'd get pq squared divided by pq to the minus 3 would be 0.048 divided by 150. Well, actually, the p will cancel, and then q squared, q to the power of 2 divided by q to the minus 3. We subtract the powers, so that'd be q to the 2 minus 3. That'd be a double negative, so it'd be 5. 2 add 3. So then q to the 5 is 0.048 divided by 150, and then you get 0.00032. Yes, okay, that's the number there. So then q, if we if we have a root of 5, right, root 5, we get just a fifth. Quite nice, actually, just get a fifth. There we are. So q is a fifth. So then that means to find p, well, actually, we could substitute it back into either equation. Let's substitute it into here. So that means sub q into the second one. I'm going to get that 0.048 is going to be p lots of a fifth squared. So then that means that'll be equal to 0.04p. So 0.048 would then be 0.04p because that's a fifth squared. So therefore p is 0.048 divided by 0.04, which would be 1.2. And so that is my values. Q is a fifth, P is 1.2. There. Again, alternatively, you could have substituted directly. So we have these two equations, right? So we could have rearranged, let's say, the first one. So then P would be 150 divided by Q to the minus 3. Well, actually, that's 150 Q cubed. So then you could substitute that into the second equation. And then I would have got that 0.048 is P, which is 150 Q cubed, Q squared. So that'd be 150 Q to the 5. Then you could just proceed by then solving for Q there. Okay. Again, so many methods you can do there. So again, you can pick your poison, right? Whatever works best. But there we are. Okay, I'm going to get rid of this now to make room for this question here. It's a challenge question, but it's perfectly doable in my opinion. So we've got this question here. So we need to sketch the graph of y is 2 to the x minus 2 add 5. Okay. So this is just basically graph transformations. This is why I say it's a bit durable, because if you remember your graph transformations, this should be fine. Okay. So firstly, recognize that really this is 2 to the x, but then I've got some stuff happening to it, right? So if I just consider the graph y is 2 to the x, again, it has this sort of standard graph where it goes up like this, right? That's y is 2 to the x, and again, it'll pass through 1, okay? And it'll go to 0, and there we are. So that's my graph 2 to the x. Then I can then apply y is 2 to the x minus 2. If I do it here, so if I do y to the 2x minus 2, well, think about it. If we say 2 to the x is f of x, right? Then what's this doing? X minus 2. This is going to be f of x minus 2, right? So if you think about it like that, then hopefully you can see in terms of transformations, when we looked at transformations before, again, what we do inside the function we do the opposite to what we expect. What do we expect? We expect to subtract 2 to the x values, which would mean we shift 2 to the left. But we're going to do the opposite and instead add 2 to all the x values. So that means it's going to shift 2 to the right. Okay. So what's going to happen is, honestly, it'll still have a similar sort of graph, to be honest, but it would look like this. But the key idea is this point here, this point is 0, 1. Oh, didn't mean to move that. This point on the y-axis, this y-intercept is 0, 1. So if I'm adding 2 to x, then it would be 2, 1, okay? So that point would then move to 2, 1. And obviously there'll be another y-intercept, but we'll deal with that as at the end. So that's my new graph. Okay, I've just shifted 2 to the right. Doesn't look it because it's still the same sort of graph. But anyway, we shifted 2 to the right because obviously we do the opposite. Instead of subtracting 2, going 2 to the left, we go 2 to the right. Okay, then lastly we add 5. Okay, then lastly we add 5. So we have y is 2 to the x minus 2, add 5. So again, in terms of function notation, that'd be f of x minus 2, then add 5. So the 5 is outside the function of x. So that will do what we expect. We add 5 to the y values, so which means we're going to shift this graph up, all of it up by 5 units. So that means it's going to look like this. Okay, and that would be my graph. This would be y is 2 to the x minus 2, add 5. Again, I don't know what the y-intercept is. I can work that out quite easily. But yes, and then this point here, 2, 1, if we add in 2 to y, if we added 5 to y, it would then be 2, because x is still 2, at 6. Okay, 1 add 5 is 6. Okay, so that's my graph. Okay. Cool, so hopefully that makes sense in terms of graph transformations. Now, and then it just said, it asked to give the coordinates of the point where it crosses the y-axis. Okay, so it wants this point here. Again, I can easily do that because my equation is y is 2 to the x minus 2, add 5. So that means if it's a y-intercept where it crosses the y-axis, that means when x is 0. So if I set x to 0, then y will be 2 to the 0 minus 2, add 5. If I put, let's say that in the calculator, 2 to the minus 2, then add 5. That will be 5.25. So that would be my y-intercept there. 5.25. Cool. So there we are. So again, just to emphasize, you need to be comfortable with transforming graphs, okay? Because now you'd be expected to do that with exponential graphs in this way, okay? Okay, talking of graph sketching, we've got this exam question to finish off on. So we need to sketch the curve y is 4 to the x. So it's quite a standard graph actually. So 4 to the x, again, it'll be looking like a to the x in general. It would have this sort of, it would go up like this, okay? A bit nicer than that though. There we are. Y is 4 to the x, okay? And it'll pass through. Where would it pass through? If you're a bit stuck, it would be 1, but if you're a bit stuck on that, well, if we set it, that would be the y-intercept. So that means x is 0. So then y would be 4 to the 0, which is just 1, because anything to the power of 0 is 1. And so that is the intersection with the y-axis, and that's it. Okay, so that's my graph for 2 marks. Okay, that is my sketch. Okay, so that's it for exponentials. So hopefully comfortable with the idea of an exponential function. So a number to the power of x, and what the graphs look like, and how we can use the graphs to transform it, and so on. Okay, so that's it. I'll see you next time.